Now we are live, sir.
Okay. Can you just give me the YouTube link?
It's just a second. We are just adding it to the chat box, or I'll just send you to the mail. An astronomer. Today, our guest is Mr. Niruj Mohan Ramanujam. So before I introduce Mr. Neeraj to everyone, I request that all students to submit their questions to the Google form that is pinned to the chat and in the description box below in the video. Mr. Neeraj Mohan Ramanujam works at the Indian Institute of Astrophysics in Bengaluru and is the head of its Science Communication, Public Outreach and Education Scope section. He used to be a radio astronomer and had previously worked at SA Rao, South Africa, NCRA Pune, Leiden University, Netherlands, and Bengaluru, AP, France, and is the head of its science communication. He is the former chair of the outreach committees of India, ASI, POC, and Africa. Today, he's going to share his valuable insights on the mission of Aditya L1. Now, as we all know, that sun is in its extremely active form these days, so we are all excited to know more about it, sir. Now, the floor is yours, sir. You can start, please.
Yeah. Thank you so much. Thanks, Space India, for inviting me to talk to students. I can't see the students, but I know you can see me, so that's fine. As she said, my name is Neeraj Mohan. I work at the Indian Institute of Astrophysics here in Bangalore. And today I'm going to talk to you about Aditya L1. Aditya L1 is very special. It is India's first space telescope or observatory to study the sun in its entirety. So Aditya L1 was launched by ISRO on. So you might remember that for 2 weeks the newspapers and media were all about ISRO, and it was a really fun time for all of us. Aditya L1 is an observatory, which means it has multiple telescopes. So it has 7 different instruments on board, and I'll talk about them as we go along. It was launched on 2nd September. It took around 6 months to reach its orbit, and it reached its final orbit in 6th January this year. And now it slowly started functioning, with each instrument one by one. I'm not going to talk about Aditya directly right now. First, I will show you a couple of videos, and then I will tell you about the sun. I'll tell you what the sun is made of, what powers it, what are the kinds of things the sun does, which we can see through various telescopes. What are the various problems or questions astronomers study about the sun? And then I'll come back to Aditya, and then you'll have a better understanding of why we launched Aditya, why do we have the 7 instruments on board, and what do we hope to learn from these 7 instruments. Okay. So I'll ask you a couple of questions now and then, or try and find out if you already know a concept. So you can either raise your hand or say something on the chat window, which are people from Space India will then relate to me. I'll explain most concepts, assuming I think you're 6th to 8th standard. So I'll explain most of the basic science concepts as we go along. But it'll be good for me to know if you already know them a little bit. Okay. So let's move on. These are images of Aditya L1 after being assembled inside ISRO. So the golden colored thing in the center is Aditya L1 with all the 7 instruments packaged together. You might wonder why all these spacecrafts are golden in color. It's not real gold. It's wrapped with a particular metal, which is a thermal insulator. So it protects it from the extreme heat from the sun, right? And then the two curved things you see here are what are going to cover Aditya, and those will sit. The entire thing will sit right on top of the rocket. And so when the rocket launches, then ultimately when it goes up to its orbit, it will open up, and then the satellite will be pushed out into space. So let's kind of go back to 2nd September. So that was the launch of Aditya L1 on PSLV C57. I will tell you a little bit about what my own institute has to do with Aditya. There are around 10, 15 astronomers from my institute who were involved with making some of the instruments. All of them were at ISRO. I was here at that time in Bangalore, and around 10, 15 astronomers, solar astronomers from my institute, plus many other institutes in India, were in Sriharikota to witness it live, and it was a fantastic moment, of course. Now, Aditya L1 has 7 different instruments, and this figure kind of tells you what they are. One is Aspects, other is Helios, other is Papa, then there is Suit, VELC, Magnetometer, and Solex, right? And I'll tell you a little bit about each of them. So I'm going to play this video from ISRO, which talks about each payload a little bit. Now, then I'll go back to look at the sun and explain what the sun is all about. Then we'll come back to this video, and then you'll understand a lot better what the people here tell you. Okay. I'm assuming the audios can be heard. Okay. So that was a video from ISRO explaining very briefly what the 7 instruments are. Aditya, and therefore now let's go back to the sun and see what the sun is all about. At any point, if you do not understand what I said, or if you want me to explain something again, please just put that on the chat, and then our Space India volunteers will then let me know, and I'll explain it again. Okay. So if you don't understand any concept I said or anything I said, please let me know, and I'll say it again or explain it in a different way. Okay. Now the sun is a huge.
Just a second, sir.
Yeah.
So I guess the audios are not like audible to the audience. So if there are any further videos, yeah, you can also volunteer to just explain the videos by yourself. That can be
Okay.
great.
Okay. So the audio for the previous thing was also written down, so that's fine. All the remaining videos will not have any audio, so that's fine.
Okay.
Yeah,
Okay.
except for one, I will just do a running commentary myself then, right?
Okay. Please
Yeah,
continue, sir. Yes.
yeah. The launch, of course, had a countdown, so that was fantastic, and you can see that on YouTube as well. Okay, cool. Thanks for letting me know. Our sun is just a star, like so. All stars are like our sun. They are giant balls of gas, which are very hot. The sun emits energy, it emits heat and light, which is how we survive on Earth. All life on Earth gets its energy from the sun. But where does sun get its energy? Right. So at the core, a very central part of the sun, it produces energy through a process called nuclear fusion. Now, some of you might know. I think at least eighth class students would know that all matter we know is made of atoms of various elements like hydrogen, helium, carbon, nitrogen, oxygen, sodium, potassium, and so on. And at the center of the sun, it's very hot. It's a few million degrees temperature, right? And if it's so hot, what happens is that lighter nuclei, lighter centers of atoms, specifically hydrogen, come together and then stick together and form a heavier atom, or which is in this case helium. Okay, and in the process of these hydrogen centers of hydrogen atoms or nucleus coming together and sticking together to form the nucleus of a heavier atom like helium, it releases some energy. Okay, and every second trillions and trillions of such atoms come together to form helium, and therefore it emits a lot of energy from the center. This energy from the center travels outwards to the sun, and then when it leaves the surface of the sun or the outer layer of the sun, it then streams the radiation then or the light then streams outside throughout the solar system, and the light which hits the earth is what sustains life on earth and so on, right? And so this is how the sun produces energy, and all stars in fact produce energy in a similar way as well. Okay, but what is the sun made of? I said there are some lighter elements in the center fusing to form heavier elements and so on. But is sun a solid? Is it a liquid? It's a gas? The answer is no. So all of us, I think, have studied in school that there are solid, liquid, and gases. If you heat a solid, it will liquefy, it will melt, and if you heat a liquid further, it will evaporate and become gas. But there's a fourth state of matter called plasma. If you heat the gas even more, the gas is made of atoms, right? Atoms of hydrogen, carbon, oxygen, and so on. And you might have studied in school already that each atom is made of a nucleus which has these particles called protons and neutrons. And outside the nucleus is a giant cloud of electrons going around it. This whole thing is called an atom. Now, if you heat the gas very much to very high temperature, a few million degrees temperature, the electrons will come out of the atom and the electrons and the nucleus will be sucked. Okay, this is called a plasma. It's called an ionized. So you say the gas is fully ionized and therefore it's called a plasma. This very hot gas where the electrons are separate from the nuclei or the protons and neutrons. And the sun and all stars are made of plasma because the stars and sun are made of gas, but then the gas gets so hot that it becomes a new state of matter called plasma. Okay, now let's shift a little bit. This I'm sure all of you have studied in school, and any of these is new or difficult, just put on the chat and I'll go back and explain to you again. Right? All of us have seen a compass. The compass needle always points north, right? Now, why does the compass needle always point north? A compass needle is like a bar magnet, which is on the right side. And the bar magnet has a north pole and a south pole. And the magnetic field or the magnetic lines of force come from north pole and go to south pole on all sides, right? So every magnet has two poles, north and south. And every magnet has magnetic field lines or magnetic lines of force coming out of the north and going back to the south. This is called the bar magnet. Now, why does a compass point to north? Because the earth itself is a giant magnet. You can imagine that there's a bar magnet in the center of the earth pointing towards north and south. This is because the core of the earth is molten and it's liquid. Okay, and because the earth has a magnetic field, because it's like a bar magnet, it has a magnetic field. The magnetic field will go from the north pole and come back to the south pole like everything else, right? Now, because the earth has a magnetic field, the small little compass you have with you also orients itself along the earth's magnetic field, and therefore you can take this compass and go wherever you want to, almost everywhere on the earth, and you always know where the north-south direction was. And this is what people use for centuries when they're navigating the seas, when they're traveling on the water in the ships, to find out what the direction was. Okay, the Earth has a magnetic field, and therefore it has a north pole and a south pole, and the magnetic lines of force go around the Earth, just like in the bar magnet. Now the sun also has a magnetic field, and this magnetic field comes because the sun is a plasma. Now the sun, therefore, you can imagine that there is a giant bar magnet inside the sun. The right side is a picture of the sun. I'll tell you why it looks so weird in a little bit. Okay, so there's a north pole and a south pole of the bar magnet inside the sun, and therefore there are magnetic lines of force through the sun and also outside the sun. Okay, now the plasma in the sun and the magnetic fields in the sun are stuck together. Okay, they're stuck together for a reason I will not go into now. And because they're stuck together, when the plasma moves, the magnetic field moves. When the magnetic field moves, the plasma also moves. Okay. Now the magnetic fields are in loops, right? You saw on the left side the magnetic fields are in loops, and therefore when the magnetic field goes out of the sun, the plasma also will go in loop. So the gas will also move in a loop. Okay, and this is a beautiful picture. This is an example. So when this is a part of the surface of the sun, and it looks dark. I'll tell you why it looks dark later. This is a picture of the sun in the ultraviolet, and we'll come to ultraviolet a bit later. Okay, now this is part of the sun. You can see the surface of the sun curving like this, and this is the ultraviolet image of the sun, and then you can see this nice, extremely pretty loops. These are where this is like a small band magnet there, where the magnetic lines of the magnet go out of the sun and come back in, right? And because the plasma and the magnetic fields are stuck together, the plasma also moves along these field lines, and the plasma emits light, so you can see them as bright loops, right? So these loops trace the magnetic field. On Earth, if you go to your high school physics laboratory, you might do an experiment with the bar magnet iron filings, and you'll see the iron filings line up along the magnetic field. Here on the sun, you have gigantic magnets where instead of iron filings, the plasma itself aligns along the magnetic field lines. Right? This is what you see. But this keeps moving. This is not unchanging, right? The magnetic field and the plasma keeps moving in and out of the sun. As it does, these patterns keep changing. And I'll show you a very, very nice video about it a bit later. Okay. So what have we learned so far? The sun emits huge amount of energy, right? It comes from the core of the sun and then it travels outwards and then it goes through the solar system, right? The sun is made of a new state of matter called plasma, which is formed when you take gas and you heat it to a few million degrees. But the outer layer of the sun is only 5,500 degrees, right? Right now, I think summer is approaching, and at least in South India, it's very, very hot. It's around 30, 35, 36 degrees in South India already. In North India, I think it's still a bit cold, so it's probably around 15, 20 degrees. But the surface of the sun is 5,500 degrees. Okay, so it's very, very hot. The sun, we also saw, sun has a magnetic field, just like a bar magnet, just like the Earth. And the plasma, you can see the plasma or the gas flow along the magnetic field line. So that's what we learned so far. Is this okay? Can I go forward to the next topic? Or are there questions here? I'll wait for a minute. If there are no questions, I'll go to the next topic.
Sir, I don't think so there are any specific questions, but there are some comments which are saying, can we just go a little slow because there might be a fast to them.
Okay, sure. So if this
now
is
we
clear,
can go ahead. Yeah,
okay, we'll go. Yes. Okay. Now this is a video of the magnetic. So if you look at the right side on the limb outside the sun, you can see these loops. These loops, and they keep changing as the sun rotates, right? So these loops, so the magnetic field lines and the plasma with it keep changing, keep moving, and as they move, you can see these loops forming and disappearing and so on. It's beautiful, right? This is an ultraviolet image of the sun. This is a close-up of the same thing taken from a observatory in space launched by NASA a few years ago, and you can see all kinds of things happening, right? The gas is, the plasma is bubbling up, it's flowing, it's going down, it's coming up. But then they don't just go out and in whenever, however they want. They go travel along these loops. And these loops are the magnetic field lines, right? I mean, I think the sun is beautiful. It's fantastic. We never get to see the sun this way, normally in the sky. And I'll come to why that is so in a bit. Okay. Let's just watch the video. This is part of the surface of the sun. And you can see these bright spots where the plasma is extra hot. And it comes out of the sun and then goes back in and so on. Okay, I hope that video was good. Yeah. Now let's now explore this further. On the right side, you see a part of the sun, again taken by a NASA spacecraft called Solar Dynamic Observatory. Okay, and one of these so we saw these small loops. Sometimes these loops are very very big, and they have a lot of energy because, and then they can erupt. Right, they can erupt out of the sun, just like volcanoes erupt from the Earth's crust. Right, and when they erupt out of the sun, the loop gets bigger and bigger and bigger, and then it can come out of the sun entirely and then travel through the solar system. Okay, these are called solar storms. Just like we have storms on the Earth, we have cyclones on Earth, we have storms on Earth where the wind moves really, really, really fast, right? Same way on the sun, when these loops have become very, very big and they have a lot of energy in the loops, then they start traveling at great speed, very, very high speed. And when they do that, they can break away from the sun, and then they become what we call a solar storm or a sun storm. And these solar storms then blow outwards through the solar system in the space between the planets. Okay, look at this. You can look at this image and see how small the Earth is. Right? So these solar storms are massive. Right? There are some 10, 20, 50 times as big as the sun, as the Earth. Right? And therefore, sometimes they can blow past the Earth. Right? And that is why we have Aditya launched to study the sun. Okay. Now I'm going to show you another video of such storms. You see? I'll show it again. So some of it goes back, a lot of it then goes out of the sun, right? And those are solar storms. I'll show you another example. On the left side, it's a picture from another NASA spacecraft called SOHO. Now, what they've done is that the sun is very, very bright, right? So if you want to see what happens outside the sun, you have to block the sun, like an eclipse. You have to block the sun, okay? And then then you can see fainter stuff around the sun. So that's what they've done here. So the circle, the maroon circle, the solid circle, is to block the sun. It blocks the sun. It's a bit bigger than the sun, and the white circle is where the sun actually is. But then you block a larger area, right? And then you can see all these light coming out of the sun. Those are all storms, solar storms, or solar flares coming out of the sun. And I'll show you a video taken. So they take an image every few minutes and put them together to make a very short video of a longer duration. Right? So this whole video I showed you just now, I'll show it again, was taken over 6 hours. So they took images every hour or every half an hour over 6 hours. You can see the timer at the bottom, and then they compress the whole thing into one small video. Okay, so if you look at the time, it's 23:06. It ends at 6:54. So it's around 7 hours, 8 hours, right? Now, what did you see here? You saw that the storm erupted from the sun. It traveled out of the sun, and then it just went out, right? So that's what solar storms do. And then they'll just travel in the space between planets, and some of them, if the correct direction, can also hit the Earth. I'll show you one more example on the right side. Right? So look at what the sun, see? Again. So sun is not this quiet ball of fire in the sky which doesn't do anything, just shines continuously. It's a very active place. If you look at the sun in ultraviolet or other wavelengths like this, it's a very active body. It emits light, but then it also ejects plasma. So part of it, and when they eject the plasma, these solar storms which come out, they can have billions and billions of tons of matter, right? And they're thrown out of the sun with very high speed, and then they travel through the interplanetary space. Right. Now, I will show you one more video from NASA. There is no audio for this, so that's fine. This is again a close-up. This is again sped up a lot. So you take images every half an hour over a whole day, and then you speed it up a lot to create this video, right? So this video actually is over a few hours. So you can see the kind of violent ejections coming out of the sun, which you need to go to space to see, because from Earth it's very difficult to image these things. You have to go to space to image this kind of activity, these solar storms and solar flares and coronal mass ejection. The various names for them, depending on the kind of ejection, there are various names for them. Okay. How many of you think this is really cool? Or do you all seen this before and it's like very normal for you? If you think it's really, really cool, you can say so on the chat window or you can raise your hand.
I myself think it's extremely cool, sir.
I mean, every time I see this, it's amazing, because I look up at the sky and the sun. I mean, we're used to the sun, right? We see it every day. But then we have no idea sun does all these fancy, all these incredibly crazy things, right? And look at the size, right? The Earth would be extremely small, right? So these storms where they eject so much plasma are like 50, 100 times as big as the Earth. Right? Can you imagine storms that big? If you think it's cool, raise your hand or say so in the comment. Okay. If you don't think it's cool, that's fine. Right. Now, I said that these storms, you saw storms which are very, very, very energetic. A lot of energy in the storms. So they can travel very fast and go very far. Right. And sometimes a storm is in the right direction, it can hit the Earth. Now, nothing major happens. I mean, some things can happen. Right now, the Earth has a magnetic field. We saw already. The Earth's magnetic field protects us from the solar storm. Okay, if it wasn't for the Earth's magnetic field, the solar storm will hit the Earth directly, and then there'll be a lot of problems. Right now, our magnetic field protects us from all of these insane things the sun does. Right, but then some of the solar storm particles do enter the Earth through the north and south pole, of course, which is what is shown in this figure. But they can still, even if they are protected from hitting the Earth directly, they still can do a lot of damage. For example, we have satellites going around the Earth in orbits, which are some of them are around 250 kilometers, some of them are 6,000 kilometers, and so on. And the solar storm, remember, carries plasma. It has plasma and it has very strong magnetic fields. So when these plasma and strong magnetic fields in the solar storm or solar wind hits our satellites, it can damage the electronics of the satellites. Right? So there are examples where satellites, the electronics have been damaged beyond repair sometimes when especially exceptionally powerful solar storm has hit the Earth. Okay, there have even been examples of solar storms. You can see the blue line. Some of them can enter the Earth only through the poles, right? And then in the polar regions you have, for example, northern Canada, Alaska, northern Russia, and so on. So there have been a couple of solar storms which are so powerful when they hit the Earth that these plasma came in, magnetic fields came in, and then they damage the power grid, right? So how do we get power in our houses? We have these. If you go outside the city, you will see these huge towers and these huge wires going for kilometers and kilometers and kilometers, right? So that they damaged them so much that the entire state in Canada called Quebec had no electricity for more than a day, right? So it downed the entire power grid. So solar storms, once in a few years, very rarely get a very powerful solar storm, which can even damage the electric grids in the northern, southern polar regions of the Earth. But they can always cause problems for satellites. And therefore, we need to understand how do these solar storms form? How do they travel in the space between Sun and the Earth? When will they arrive on Earth? How strong will they be when they arrive on Earth? And so on, right? So just like we have Earth storms on the Earth, and you have to predict the storm on the Earth or cyclone on the Earth, so that you can tell people on the coast, hey, no, go inside, don't stay on the coast, don't go out in a fishing boat, and so on. So we protect our people because we are able to predict where the cyclone comes. Same way, now we have astronomers, including in my institute, who are solar weather prediction people. Okay, so just like we have Earth weather prediction, just like that, we also have solar weather prediction. Okay, so this is called space weather. So the people working on predicting space weather. So when something happens on the sun, it takes around 2 days for the solar storms or solar flares to hit the Earth. So in those 2 days, can we quickly figure out when it will hit the Earth, how strong will it be, how much damage will it do? So sometimes when we know it hits the Earth, they even switch off some electronics on the satellites to save them, right? So therefore, predicting the solar storm and how they travel is very important. Okay. So now what have we learned now? We learned that there are huge eruptions from the sun which carry enormous energy. These eruptions are much bigger than the Earth, and these eruptions are made of plasma and magnetic fields, and they blow outwards from the sun in the interplanetary medium. and they could hit the Earth and damage our satellites and so on. Therefore, we need to be able to predict these storms. Now, I'll just wait for a minute and see if there are any questions about this before I move on.
There is one question, sir. I guess there are multiple questions. Can you explain plasma to them? There are multiple questions related to this.
Okay. So you can think of plasma. So you take solid, let's say you take ice and then you heat it, it becomes liquid water. You heat liquid water, it boils and becomes water vapor gas, right? If you take a lot of gas in some place and then you heat the gas, even these gas is made of atoms, right? So for example, water vapor is made of water molecules, which each water molecule has 2 hydrogen atoms and 1 oxygen atom, right? And if you heat this water vapor even more, the hydrogen oxygen will split and there'll be separate hydrogen atoms, separate oxygen atoms. If you heat it even more, these atoms are made of electrons and protons and neutrons together as one unit. They call it an atom. If you heat these atoms even more, the electrons and protons and neutrons also will move away from each other. You will no longer have atoms. You'll have separate electrons, separate protons, separate neutrons. That is called plasma. So you can think of plasma as very, very, very hot gas, where there are no longer any atoms, there are only particles. Particles are electrons, protons, neutrons, and so on. So you can think of, so mainly electrons and protons. So you think of plasma as extremely hot gas, where the atoms break apart. Right? That's all. And these plasma are also have magnetic fields in them, and therefore, since the plasma will move out of the sun and past the Earth, the magnetic field also will hit the Earth, and these magnetic fields can damage our satellites and power grids. Is that okay? Is that clear?
Yes, sir. I think it would be very clear to them now. Thank you.
Okay.
I think we can go ahead, sir.
Okay, so let's go on to the. So I showed you all these pictures, and the sun was looking really weird, right? It was looking dark. It had holes. It had bright spots. We know sun doesn't look like that. Now let's see. So the top pictures, how the sun looks like to us in the sky, right? By the way, do not ever look at the sun directly. Don't look at the sun with your naked eyes. It's not good for your eyes. Never look at the sun through a telescope or binoculars. You will damage your eye permanently. Okay. Now we can look at the sun a little better when it sets or when it rises, of course, because then it's not as bright. And at the bottom, you see a typical sunset photograph. You can know. So you see, sun is a disk, it's a circle, it's a sphere, but it looks like a circle to us on the sky, and it's a uniform disk of light, right? It just looks like somebody just painted uniform yellow everywhere. It's a uniform disk of light. But I showed you all kinds of stuff. Now, if you look at the sun, if the same sunlight you see here, if you then project it safely through a telescope and take a photograph, and you should not do it at home, but astronomers know how to do it safely, then you'll see things like this. Okay. Now you'll see that the sun is not a pure white disk or a sphere. It has some dark spots on it. Okay. Now these dark spots are called sunspots. Now, why is the sun very bright? The sun is so bright you can't even see to the naked eyes, right? It's so bright because it's so hot. And therefore, if the sun is even hotter, it will be even more brighter. The sun is cooler, it will be less bright. Now, these spots on the sun are cooler plasma. The sun's surface is roughly 5,500 degrees temperature, but these sunspots have gas or plasma. It's only 4,000 degrees centigrade. 4,000 degrees is very, very hot, but the surrounding region is 5,500. Therefore, in contrast to the surrounding region, which is much hotter at 5,500, these spots look dark. If you could take a sunspot and put it outside the sun, it will be very bright by itself. But because it is in the middle of a much brighter area, it looks very dark. And these sunspots come and go, and we've been studying these sunspots since 400 years, around 420 years. Now, why 420 years? I'll tell you in a bit. Now, this thing you see, this with dark spots, it's a very special photograph. It's a photograph of a hand drawing. Okay, and this is a photograph of hand drawing of sunspots made by Galileo Galilei himself on 23rd June 1630. Right, so it's around 410 years ago. Right, so because telescope was invented around 1610 and so on by Galileo. Then he started looking at the sun, and then he started drawing these sunspots. Okay, so this is actually a drawing made by Galileo, which I think is really cool. That we have his observation records, we have his notebooks, we have his log books, right? So I thought it's pretty cool. Now, if you zoom into the sunspot with modern telescopes, which are much, much better, a sunspot which you see there would look something like this. Okay, and this is amazing. This is brilliant. Just zoom into a sunspot. Really, you see a dark center, you see a less dark outside region, and then the yellow part is the regular surface of the sun. Okay, on the but then so I showed you Galileo's drawing. Astronomers have been drawing the sunspots and photographing sunspots for more than around 400 years now. In India as well, we've been doing it. So in India, in 1899, there was an observatory set up by the British in Kodaikanal in Tamil Nadu called the Kodaikanal Solar Observatory. Okay. In fact, this year, and the Kodaikanal Solar Observatory is an observatory of our institute where I work. So it is one of our observatories. And we are going to celebrate its 125th anniversary this year. Okay. So it's a very, very old observatory. It's 125 years old. So on the left, I'm showing you a drawing of the sun taken from the Kodaikanal Solar Observatory in Tamil Nadu on 6th April 1904, which is, really old, right? I mean, these things, I just love this. So you can see these small spots somebody's drawn by hand, right? They're all sunspots. On the right side is the image of the sun taken by the same Kodaikanal Solar Observatory yesterday. And you can see at least 4 different groups of sunspots, right? So this is an image taken yesterday from Kodaikanal. I downloaded it from our website. You can go to our website and you can download the daily image of the sun. And this is how it looks like. So you see 4 groups of dark spots called sunspots. Okay. Now this is a zoom in of another sunspot. Now these sunspots basically occur because certain parts of the sun suddenly cool down, and then therefore the sunspot gets created. And after a few days, the plasma moves into it and it becomes hot again, and then it disappears. Okay. So when the cooler sunspot becomes hotter again, it will disappear and then it won't look any different. Therefore, smaller sunspots will last for a few days. Larger sunspots will last for a few weeks. Okay, now I'm going to show you again the space observatory launched by NASA. It took photographs of the sun every day, and then you put them together over a whole month of February 2013, and you can see how the sunspots move. Now, you might or might not know. I don't know how many of you know. If do you know the sun rotates around its axis? If you know that, say so. Put on the chat saying, I know the sun rotates. Okay. The earth rotates around its axis once in 24 hours. Same way, the sun rotates around its own axis in 30 days. Okay. If you knew this, say yes. Now, as the sun rotates once in 30 days, the sunspots will also rotate along with it. Okay. And after a few days or weeks, it will disappear, but new sunspots will come. So now let's look at a video and see how these sunspots appear and disappear as the sun rotates around its axis. This is a lot of images taken every day put together to make a time-lapse video. Okay. You can see sunspots appearing and then disappearing, right? And so smaller sunspots disappear very quickly. Larger sunspots take longer to disappear. Sunspots move, they become big, they become small. And you can see this changing because the sunspots move because the sun itself rotates. So I'm going to show it again. If it is not clear why the sunspots are moving because the sun is rotating, just stay so and I'll explain it again. Okay. So just like when the earth rotates, the cyclones and things on the earth rotate along with it, and the cyclone disappears at some point, new cyclones appear. Same way, as the sun rotates, sunspots appear on its surface and then they disappear again. Okay. I'll show you one more time-lapse video taken about one big sunspot group, which was followed by the same space observatory launched by NASA. This was the sunspot group in 2012. You can look at the date at the bottom, 2012, 17th November. So you can see sunspots forming, becoming bigger, moving away from each other. Smaller spots disappear, more smaller spots come in, and so on. And this is a large sunspot group, so this will probably last 2 weeks or 3 weeks, right? Smaller ones will disappear faster. Let me show it again. Smaller ones keep appearing and disappearing. Sometimes They merge, become larger sunspots. The sunspot can grow, become really large. Then when it becomes really large, then they move away from each other. They can split up into smaller ones. They change their appearance. So this is over a day. So you can see the counter at the bottom, right? And so it tells you the it's 2012, 11, 22 means 22nd November 2012. So as every day passes, they keep changing. Right? This is another example. Again, the sun is looking weird because of ultraviolet, but then you can see a solar storm, right? Which again sped up massively. You can look at the timer at the bottom. Right? 28th October 2021 starts at 3 p.m. and then it ends at 4 p.m. So in 1 hour, it emitted a very strong storm. It just went outside like an explosion. These are explosions, right? These are plasma explosions. Now, let's look at one more thing and then we'll put them all together. Okay. Now, I'm sure all of you have seen total solar eclipse pictures. If you've seen a total solar eclipse or an annular solar eclipse, I want you to say so on the chat window. There was an annular solar eclipse in 2000, I think 2019, and there's one in 2020. One went through southern India, other went through northern India. So if you've seen a solar eclipse, do say so on the chat, and I request Space India people to tell me if there have been some students who've seen an eclipse themselves. Now, a total solar eclipse, of course, happens, like all of you know, when the moon comes between the sun and Earth. The moon then exactly covers the sun, and then for a few minutes, and that's a total solar eclipse, right? And you get a total solar eclipse a few times a year, maybe twice a year, up to 7 times a year in different parts of the Earth. Now, when the moon covers the sun, you might have seen these pictures. Then you have this weird diffuse glow around the sun, right? This glow is called the corona, and this corona is the atmosphere of the sun. Okay, so you hide the sun, and then you see the atmosphere of the sun. Why don't you see it every day? Because the atmosphere of the sun is a few million times fainter than the disk of the sun. The disk of the sun, we all know, is extremely bright. And therefore, if you want to see something with a few million times fainter, you have to cover the disk of the sun, right? Just like, for example, you have some headlight coming, a floodlight from a stadium, and you want to see somebody holding a small candle. You need to cover the floodlight to see the candle. Same way, you need to cover the sun to see the atmosphere or the corona, which is very, very faint. How do you cover the sun? You put the moon between us and the sun. So when the moon comes exactly in between, you can cover the sun. You can see an eclipse. So did people are there students who have seen an eclipse? Did people say they have?
Right now, sir, they're asking about will the sun's heat will damage Aditya L1? They are
Good question. Very, very good question. And I will come to that later in the talk.
Yes.
Yeah.
So
meanwhile, tell me, please. Yeah.
Meanwhile, the students, whoever is watching, can answer sir's question that have you seen any eclipses till now? You can answer that in the comment box.
Any solar eclipse or even lunar eclipse. Yes. A lunar eclipse is when the Earth's shadow falls on the moon and the moon becomes dark, right? So have you seen a solar eclipse or a lunar eclipse?
If you have seen so, you can put that heart button in the corner. You can press it on that and I will get to know it.
Yeah. So these pictures are from 3 different total solar eclipses. TST means total solar eclipse. Total solar eclipse is when the moon exactly covers the sun. So on the left, there's an eclipse from 1999. In the middle, there's an eclipse from 2017. On the right side is a very special eclipse. Please note the year. It was an eclipse which was seen in southern India. At that time, before independence, there was something called the Madras Observatory in present-day Chennai. Okay, and the Madras Observatory was set up in 1786. 1786. So more than 200 years ago. And that observatory then now became Indian Institute of Astrophysics, where I work. So my institute, in some sense, is more than 200 years old. Okay, in 1898, which is more than 100 years ago, there was a total solar eclipse visible in India, in I think Andhra Pradesh and so on. And therefore, a group of astronomers, British astronomers from Madras Observatory in Chennai, traveled there, and then they took this photo. And we have put the IAA logo on it as a logo for the Aditya L1 instrument, right? So astronomers have been chasing total eclipses for centuries, because that's the only way you can get to image this corona, this very, very faint corona of the sun's atmosphere. And that is the lesson I want to tell you. So astronomers want to see the corona. And so far, they've been able to see the corona almost only during total solar eclipses, which is a few minutes a year now and then. And therefore, you have to travel to where they are. And so this is something people have been doing for a long, long time. So how many have seen eclipses? Do we have a number now?
Yes, so we do have a lot of number, and many of them have seen both, and some of them have seen solar, not total, partial, and some have seen lunar. And we have a multiple audience who have seen the eclipses.
Fantastic. I'm very happy to hear that. Because total solar eclipses are, I mean, some of the best things you can see. If you want to, you can go and see Niagara Falls, you can see Aurora Northern, you can see some very special, you can see Taj Mahal, you can see, some rainforest in Amazon. Total solar eclipses like that. If you see it once, you'll never forget it. It's just an amazing thing to see. It changes your life, right? It's a totally new experience, which if you have a chance, you should never, let go. You should go and see it. Okay. So what have we learned so far since the last series of slides? So we know that there are dark spots that form on the outer visible layer of the sun. These are called sunspots. Now, these spots last for a few days to few weeks. Okay. If you look at the number of sunspots you see on the sun every week or every day, and you count them, I didn't show you data for this. If you look at the number of sunspots every day, okay, and you plot them day after day after day after day, month after month, year after year, the number of sunspots will slowly increase, right? And then they'll decrease, then increase again, then decrease again, increase again, decrease again, and so on. And the time it takes to increase and decrease once is 11 years. Okay, this is called the 11-year solar cycle. It's very important. Okay, I won't tell you any more about this, but then there's something for you to know. The number of sunspots, and therefore the number of sunspots on the sun has a cycle. The number of sunspots varies from low to maximum to low to maximum every 11 years. But the thing is, sunspots are also associated with these solar flares and solar storms. And therefore, the number of solar flares and solar storms also follow a 11-year cycle. And right now, we are in the middle of the maximum, right, of the current cycle. Therefore, if you see the sun any day now, this year, you will always see sunspots. And there are more and more solar storms coming. In fact, I don't know if you remember from the news, Elon Musk had launched 40 satellites at one go last year, the part of the Starlink, right, from SpaceX. And they did not calculate correctly the effect of a solar storm hitting. Now, it so happened that they were hitting the Earth, and a very powerful solar storm hit last year. And then because of that, the satellites got damaged in some sense. I won't go into why. And all 40 satellites spiraled into the Earth's atmosphere and burned up. They lost all 40 satellites, 41 satellites, because of a solar storm. So solar storms can actually have a big effect on the Earth, right? And because right now we're in the middle of the maximum of the current cycle, 11-year cycle, we have a lot more solar storms, lot more sunspots, lot more solar flares every week. Okay, and therefore it's also important to study the sun over many, many, many years to find out how it behaves, right? So you have to study it, because we found out there are sunspots which change appearance over a few hours. There are solar storms which come every few hours. These solar storms move through the solar system in a few days. Big sunspots last for a few weeks. And then there's also 11-year cycle. So we have to keep looking at the sun all the time to understand. Right? That's the idea. Okay. Now I'm going to go a little bit back into physics. Now I don't know if you all have. Do you all know about? Have you heard of? Have you done light in your physics course? Do you know light is an electromagnetic wave? Have you done waves in your physics course? Do you know what a wave is? Do you know what wavelength and frequency are? You can just say yes, no, thumbs up, thumbs down. Okay. Meanwhile, let me just go back to basics anyway. Now, we all know what waves are in our daily life, right? There's a water wave. If you hit your hand on a swimming pool or in a bucket of water, there's a wave going up and down, right? And sound is also a wave. If I say, it kind of travels through the air, and that's a wave in the sound, wave in the air. So waves are things which go up and down and travel. Okay. Now, the various kinds of waves, right? There's a water wave, or even tsunami is a kind of wave. Earthquakes are a kind of wave. Earthquakes are waves which travel through the Earth's crust, right? And then sound is a kind of wave. Sound is a wave which travels through air, and that's how I hear you and you hear me, right? Same way, light is also a wave. Light also goes up and down. Now, what goes up and down? I'll answer this question. Okay. Now, light, no, all waves, be it a water wave or an earthquake wave or a sound wave or a light wave, can be described by wavelength. Okay. This wavelength is a number. So the wave goes up and down, up and down, up and down. The distance between two consecutive ups or two consecutive downs is called wavelength. Okay. And the frequency is just like wavelength, but it's 1 over wavelength. Okay. So shorter the wavelength, higher the frequency. Longer the wavelength, then shorter the frequency. Okay. Now we'll only talk about wavelength, so you can ignore frequency. Forget frequency. Okay. Just for you to relate to what you already studied in school. Now a wavelength can be very short, then you have a short wavelength light, or short wavelength sound, or short wavelength earthquake. If the distance between two ups is very large, long wavelength, then you have long wavelength earthquakes, long wavelength sound, long wavelength light. Now, we all know what wavelength and frequency mean in sound, right? If you say, that's low frequency. Say, that's high frequency, right? So, what it distributes between and is called the pitch, right? So, you say, you have a higher pitch, right? So, women singers, for example, have a higher pitch than male singers, and so on. This pitch is nothing but frequency. So, when I say, that is lower frequency or longer wavelength, we say, that is higher frequency or shorter wavelength. Okay. Same way, sound also can change its wavelength. Okay. Now, we all done this also. If you put a prism, have white sunlight, we'll break it up into colors. We call it Vibgyor. We've seen it in rainbows. If you've seen a rainbow in the sky, again, say thumbs up. I hope all of you have seen rainbows in the sky. They're beautiful phenomenon. And a Vibgyor stands for violet, indigo, blue, green, yellow, orange, red. Okay. Now, we know them as colors, right? But these colors are nothing but wavelength of frequency. That's all. Okay. Now the light wave, which has very small wavelength, the shorter wavelength or higher frequency, our eye looks at it as violet or blue, perceives it as blue. If you then take this light wave and then you make the wavelength larger and larger, the violet light will become blue, the blue light will become green light will become yellow light will become red. Okay. So as the wavelength keeps getting longer and longer, the violet light will slowly become red. Okay. And this is so color is nothing but wavelength or frequency. That's all it is, right? And our eye perceives different wavelengths or frequencies of light as color. Okay. Now, but then, so and how? What is the wavelength of light, right? If you look at a typical wavelength of light, it is around 500, 600 nanometers. 1 nanometer is a millionth of a millimeter. Okay, it's a billionth of a meter. So you have it's a very, 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 very small wavelength waves, extremely small wavelength waves, light, which we see with the naked eye, right? So typically it's around 500, 600, 700 nanometers, and therefore it's typically a micron, basically. Okay. Now, I told you if you take violet or blue light and you expand the wavelength, make the wavelength longer and longer and longer, it will become red. Now, what happens if you make the wavelength even longer than red? There's nothing beyond red. We can't see anything beyond red. Or what happens if we take violet light and make the wavelength shorter and shorter beyond, no, even shorter than violet? We can't see anything. But that is only because our eye can't see anything. Our eye cannot see light whose wavelength is longer than red or shorter than violet. But they exist. Okay. And any light which has wavelength longer than red is called infrared. Okay. And if you take infrared light and make it even longer, it's called microwave. And microwave is exactly what you think it is. The radiation inside your microwave oven is just light whose wavelength is much, much, much larger than the light we see with the naked eye. You take microwaves and you make the wavelength even longer, then they become radio waves, right? So what the radio waves which you get from your satellite dish or something is exactly this. Same way, if you take violet light and you make it smaller wavelength, it becomes ultraviolet. If you make it smaller, it becomes X-ray and then gamma ray. That's it. That's all it is, right? So this image, this figure also shows the same thing. So as you go from radio to microwave, infrared, visible, ultraviolet, X-ray, gamma ray, they're nothing but light with different wavelengths. Now there's no reason why an object will look the same. Now we've seen the sun invisible. I told you have sunspots, you have a yellow disk, you have sunspots. But the sun looks very different in other wavelengths, right? So the sun looks very different in infrared. Optical telescope, we know how they look. Pure white or yellow with sunspots. In ultraviolet, it looks very different. X-ray, it looks very different. Okay. And the photos I showed you of solar storms were taken in the ultraviolet. Because the sun looks very different in different wavelengths, we have to have telescopes for every wavelength. We need to have infrared telescopes. We need to have optical telescopes. We need to have ultraviolet telescopes. We need to have X-ray telescopes. Now, ultraviolet and X-ray telescopes, you have to put them in space because our atmosphere absorbs all the ultraviolet X-ray from the sky. I know I'm kind of almost hitting 1 hour. I'll try to wrap up in the next 5-10 minutes. So what have we learned so far? Light is a wave like sound. It can be described by its wavelength. The visible light that you see on the eye is just one kind of light. Different frequency or wavelength light we see as color. But then you have also light which has much larger wavelength and much smaller wavelength. These are called radio, ultraviolet, X-ray, so on. The sun looks very different in different kinds of light, and therefore we need to study the sun and all of these lights to fully understand it. Okay, is that clear? I'll move on, but then if you have questions now, type in the questions and I'll answer it in a minute.
Yes, sir. Okay, so we are just going to reach towards the end. So meanwhile, students can put their questions in the Google form that is pinned in the comments. Then we can take up after this session.
Perfect.
Sure, sir. Please continue.
So this is the same video I showed you before. Now we'll go back to this video and try and understand it, right? So this video has 7 instruments, I said. Now, one of them is the visible emission line coronagraph that's made by our institute. A coronagraph, this looks at the sun in the visible light, like what we see with our eyes. It creates an artificial solar eclipse inside the box. Okay, so we call it eclipse in a box. So this instrument which we made here has something inside which hides the sun exactly, so that you can see the corona all the time. So you don't need to travel to different countries, different continents once every few months to study the corona. You can study the corona 24/7. You can look at the corona 24/7 with this instrument because it creates an eclipse. And then you have soot, which images the. Wait, hold on. I think I'm talking slower than the video. So let me just. This is what I told you about. This is the eclipse in a box. Okay. So this is the corona. You can see this all the time now. The surah. Sorry, I'm really sorry. The next instrument is called the soot, or the Solar Ultraviolet Imaging Telescope, made by an institute in Pune. This images the sun in ultraviolet. Now by now you must be experts in understanding why we need ultraviolet telescope, because only in ultraviolet you can see these solar storms coming out, like all these pictures I showed you, right? And therefore this is a very important instrument. So we have the first instrument to look at the corona, second instrument to look at solar storms in ultraviolet, right? Okay, and then the third instrument is called aspects. Okay, and the next instrument. So I told you, right? The solar storms pass through the interplanetary medium and they can hit the Earth. Just before they hit the Earth, they'll hit Aditya, right? So when they hit the Aditya satellite, it will measure the plasma properties where Aditya is. So it will measure the plasma temperature, plasma density, magnetic field, etc. When this plasma goes past Aditya. So this instrument does that. So aspects is sitting there to measure the properties of the plasma along with Papa. Papa and aspects together measure the properties of the plasma. What is the temperature? What's the density, etc. As it sweeps past Aditya L1. Okay. Then Solex and the next instrument, Helios. Okay. Solex and Helios are X-ray telescopes. So it will image the sun in X-ray. So now what do you have? You have an optical telescope to look at the corona. We have an ultraviolet telescope to image the sun. We have 2 X-ray telescopes to image the sun in the X-rays. We have 2 instruments to measure the plasma properties like temperature, density. And finally, you have, okay. And then finally, the 7th instrument is a magnetometer. This measures the magnetic field of the plasma as it goes past Aditya. So these are the 7 instruments. I think by now you should understand exactly why we need the 7 instruments, because you know that with each instrument, what are we going to study or learn about the sun. Okay. Now we also learned Aditya L1 is called so because Aditya means sun, right, in Sanskrit and Hindi and other languages. And L1 is because it's put in a place called L1. I won't go, we are I think almost over time, so I'll stop very soon. So the sun is 15 crore kilometers from the Earth. Okay, the sun is here, Earth is here, distance 15 crore kilometer. It's called 1 astronomical unit. This is the Earth. The Aditya L1 is very close to the Earth. So this diagram is not to scale. Very close to the Earth. It's only 15 lakh kilometers. So it's 1/100th the Earth's sun distance from the Earth, but it's pointing towards the sun. The reason it's in this point called L1 is that it can always look at the sun. As the Earth goes around the sun, this L1 will also go around the sun, and therefore there's no night and day for the spacecraft. It will always look at the sun. It's always daytime, right? So it's very, very close to the Earth, but towards the sun as the Earth goes around the sun. So sun is 8 minutes away. By 8 minutes away, I mean if the light from light travels at very, very high velocity. It travels at 3 × 10⁸ meter per second. The sun is so far away that it takes 8 minutes for light to reach Earth. From Aditya L1, the light or radio waves from Aditya L1 will reach Earth in 4.8 seconds. The moon is even closer to the Earth than Aditya L1. From there, it only takes 1.3 seconds. Okay. Now, therefore, we don't look at this. I will skip this. So, aspects and Papa will measure the properties of the plasma as it hits Aditya L1. These 4 payloads will look at the sun in visible light, ultraviolet, and X-rays. So, we have 4 telescopes and 3 plasma measuring devices. Okay. Now, I'll talk a little bit about VELC for a couple of minutes. The visible emission light coronagraph is eclipse in a box. The eclipse in a box was made by us in IIA along with ISRO in our center in Hoskote, which is around 1.5 hours from Bangalore. Okay, and we had to build an international quality clean room to make the space. So this is VELC after everything is been put inside. Inside the box, there are some 40 different optical elements. There are mirrors, lenses, prisms, gratings, measuring devices, CCD cameras. The 40 such elements aligned very, very precisely. And inside this box is where the total solar eclipse happens all the time. Okay, these are the images. After it's wrapped up in this foil, is what you see on the top left. On the top right, you see mirrors and detectors and so on. On the bottom left is a vacuum chamber where we test the devices. You put the devices, heat it up, and have vacuum, so you simulate the space environment to make sure it works. Now SOOT is the ultraviolet imaging telescope, and they released images of the sun 2 months ago. And this on the left is actually a small camera. I didn't know they had this camera. I think this is the most brilliant video ever I've seen from Aditya. So there's a small little camera sitting outside Aditya L1 on top of it. Okay, and on the right side, the thing you see is the door of the ultraviolet telescope. On the left side is the door of the coronagraph, or the one which we made in our institute. And then it was opened. See, isn't that beautiful? So the door of the ultraviolet imaging telescope opened. Okay, and then it clicked the various images of the sun in ultraviolet. This is what you see on the right side. The right side images are actually images taken with this telescope around 2 months ago. They are different color. The colors are all completely false color because ultraviolet. And I think in 2 or 3 weeks, the left-hand side door is going to open for the coronagraph. We're all very excited about it. Okay. All other instruments, all the 6 instruments of Aditya are now functioning. They've been switched on. They're all working. They're sending data. And the last instrument to be turned on will be the VELC or the coronagraph sometime this month. So, there are some astronomers in my institute who are sitting there from 9 o'clock to 9 a.m. to 9 p.m. looking at the data coming in. They're getting ready for the door to open, and everybody is like super excited. Okay, the last one. So I want to tell you a little bit about my own institute. The headquarters is in Bangalore. We have observatories across India. Our most famous observatory is in Hanle in Ladakh. We have an observatory in Kavalur in Tamil Nadu. We have the solar observatory in Kodaikanal, which is 125 years old. We have a radio observatory in Karnataka, again, 2 hours north of here in Gauribidnor. And we have a center in Hoskote where we make space payloads. Okay. Lastly, so I'm from the outreach section. We conduct online talks. We have school and college visits to our observatories. We create videos and posters which are there on our YouTube channel. We have in-person outreach events. And this is open to everybody and free of charge. And you can follow us on Twitter, Instagram, YouTube as IA Bengaluru, on Facebook on IA Bangalore. And this QR code is for our WhatsApp announcement group. Only I can post, nobody can post. So don't worry, there won't be good morning messages ever. And from anybody. And you can click the QR code now and you can join the WhatsApp group. And with that, I will end. This is a picture of our observatory in Hanle, Ladakh. I'll put the QR code on the screen for some more time for you to click on it. Thank you so much. I'm sorry I kind of exceeded time by like 10 minutes, but yeah, I'll end here.
No worries, sir. It was amazing. Thank you so much. Especially when you talked about everything in detail from starting from the basics to the high ends also. So I really like that point where you explained from the video that suit feature of the Aditya L1. It was very
Yeah,
much
the
informative.
door opening was amazing.
Yes,
Goosebump,
exactly.
goosebump moment, right? I mean,
Yeah.
it's like it's as if the alien was sitting on top of Aditya and photographing it. I loved it. It's brilliant. Yeah.
Thank you so much, sir. It was amazing. Okay, so we shall now move to the next part of the session where we will ask the students question on their behalf. And now,
Sure.
students, this is your final chance to ask your questions. Remember to submit them in the Google form. I am taking the questions now. So now let's begin from the very first question.
Mhm.
So starting from the very journal question, it's from Navya Agarwal, who's in class 7th from
Mhm.
KR Mangalam Vikaspuri.
Yeah.
Now, the student is asking, who is Aditya L1 named after? Now, we know that L1 is the point, but is there any specific Aditya that we are
Aditya
using?
means sun. Aditya means the sun. That's all. And L1 is where it's sitting. So it's like saying, no, Neeraj Bangalore. Aditya L1. Yeah. Yeah.
Okay, so now we have Om Dev from 7B class from
Mhm.
St. Kabir School. Now he's asking, is Aditya L1 more powerful than Parker Solar Probe?
Okay, so Parker Solar Probe, for those who don't know, it's a solar observatory launched by NASA a few years ago. Okay, now NASA has other space observatories from where I showed you other videos and all that. These orbit the sun along with the Earth, right? Like SOHO, SDO, and so on. Parker is very different. Now you might or might not have heard of the Greek story of Icarus. Icarus was this guy. There's the Greek mythology. He wanted to go see the sun, right? And his father said, no, no, don't, you'll die. He's like, no, no, I will go. And then he then made wings. From this is the story, it's mythology. Wings from wax, and then he flew up. And then as he went near the sun, the wax melted, and then he fell and died. Parker Solar Probe is a bit like that. Okay, so Parker Solar Probe went to the sun, and it went closer and closer. It kept to the sun. It kept orbiting closer and closer and closer and closer and closer. It's still doing that. Okay, at some point, it's going to get close enough that will just melt. Okay, but then we never gone that close to the sun. And the idea is that right now it's sending amazing data from very, very close to the sun, which we never go otherwise. At some point, when it goes too close and it gets too hot and it will melt, it's gone. But just before it melts, it's going to send amazing data because it's going to go very, very close to the sun. So that's Parker Solar Probe. It's a very different kind of probe. It's sent to the sun. It's a suicide mission. But then it's going to send a lot of data before it kills itself. Aditya is going to sit near the Earth and look at the sun 24 hours a day, constantly. So it's a very different kind of experiment.
Okay, thank you, sir. So now, since we're talking about melting of the probe, now there is many questions related to that. So one of it's by Devyansha Agarwal from class 6A of GD Goenka Public School. Now she is asking, like, what is the name of the material which is used to make the satellite, which does not actually melt the heat of the sun by the
Okay.
heat of the sun?
So each instrument, each of the 7 instruments have their own protection. Okay, that's the gold-like thing you saw. So if you look at the coronagraph, for example, which is made here, the golden. So all satellites you would have seen have this gold color thing. It's called MLI, multi-layer insulation. It's not made of gold. It's made of some alloy, some metal, which reflects off a lot of light. Okay, and does not get hot, and therefore it doesn't get hot. It cannot pass on the heat inside, right? And therefore it keeps the inside cool. So therefore most of the heat which comes onto the satellite is reflected away by this gold-like thing, and therefore it doesn't allow most of the heat to enter and come into the spacecraft. The spacecraft is sitting, so it's completely wrapped up by this gold thing, right? Except for the small window, you want the light to go into the telescope, so you have a small window where the light goes in. Right? You saw the door opening, right? So, for example, the coronagraph, when the door opens, the light will go in, and the visible light is very, very, very strong. We know it, right? We know how strong it is. It's very, very hot. So, what happens is that it's going to, but then the coronagraph images the corona, therefore it blocks the disk of the sun, right? And therefore, it blocks. It's the total solar eclipse. The moon blocks the sun, and then you can see the corona. Now, the point is, we block the sun light inside the box. The light is still going to be there, and the heat is going to be there. Instead, what it does is that it has a mirror, and I'll show you that. Maybe I should not have stopped share screen. Yeah, do you see my screen again?
Yes, sir, we can.
Okay, perfect. So if you look at the top right, you see a mirror with a hole. Okay, so what happens is that the sunlight from outside hits this mirror. Okay, the actual disk of the sun, which emits most of the heat and light, passes through the hole and it's radiated outside the spacecraft through another mirror. So it goes out of the spacecraft. Okay, and then the coronal light only gets reflected from the top right mirror into the box to analyze it further. So most of the heat is let out. On top of that, on the left, you see these aluminum sheets, right? These white color sheets. Those also are very, very good radiators. So they also radiate heat. So Aditya, so there's a multi-layer insulation which is gold colored, which prevents a lot of heat from entering. And then there are ways of throwing out the heat from a mirror. And then there are coolant, the radiators which cool it, those white sheets. In fact, this cooling works so well that we need to heat the coronagraph. Okay, so the coronagraph inside is so cool that the instruments need to work around 22 degrees centigrade. And it gets much cooler than that because all this works so well. So actually, there's actually a heater inside the coronagraph to actually heat it to 22 degrees and keep it there. So it actually, so they know how to do this well. So that's how you protect it.
Okay, I think it will answer a lot of questions that I have. Now,
Mhm.
moving on, there is Lavrita Gupta of class 8
Hi.
from Manav Rachna. So she's asking, what is the most unique part of Aditya L1 do you like on behalf of your perspective?
Okay, so I didn't go into that because it gets a bit more technical, and I wanted to keep it focused on the sun. But so let me show you. Let me explain to you the two or three things which are very unique. So certain things unique about Aditya, which the solar astronomers from across the world are waiting to see. Okay, so not just Indian astronomers. There are certain things which it is unique to Aditya, which it can do, which no other spacecraft in the world has done so far. And I will try and see if I can get this asset. Okay, look at this. This is from a spacecraft sent by NASA. Now, what you see here is this red light, the inner disk, right? That is the occulter, or this is that's used to create the eclipse of the sun. Just like we have an eclipse in a box. This spacecraft also creates an eclipse of the sun, and that's the big red circle. And then the inner white circle is where the actual sun. This is a better one. So the big red solid circle is what is blocked, is that the instrument blocks that part of the sun, but it blocks a region much bigger than the sun. You see, sun is only the white circle radius, but they block a much bigger part of the sun because then it's easier, right? And then therefore you see solar storms only from outside that radius. So this orange, this the solid circle is, let's say, roughly double or three times the diameter of the sun, right? So you can only see solar storms from more than three times the radius of the sun outwards. You cannot see it inside there. So you cannot see the solar storm when it's forming or when it's just expanding. You can only see it after it crosses the occulting circle, the orange circle. And that's roughly, let's say, three solar radii, right? Three times the radius of the sun, roughly, or two times. Speciality about Aditya, especially the coronagraph, it's that this solid red circle is very, very small. In fact, it's only slightly larger than the actual sun. Okay, which means that you can now observe solar storms closer to the sun's surface than any other instrument so far. That's a huge thing about it, right? So therefore, if you can look at the solar storm closer to the sun's surface than any other instrument, then you're catching it very early in its life. And therefore, you can figure out how is it caused, how does it initially expand, how does it accelerate, etc. before it comes farther out, and then it kind of is easier to understand, right? So one big thing about Aditya is that it's going to tell us how solar storms are produced very, very close to the sun and expand. So that's one thing. Secondly, it's also going to be able to measure the magnetic field of the corona itself. Again, this is something which is very new. Okay, it's also going to measure. It's also going to measure the ultraviolet image. And so ultraviolet, again, I showed you these nice images, the very colorful images from Soot, right? Of course, the color is fake. The color is fake, but then why do I have 12 images? Because in the ultraviolet band, it has a lot of filters. Okay, so it's observing only in a narrow wavelength here in the ultraviolet. and each of these images is made from a particular wavelength. Now, there are certain wavelengths which have never been seen before, and therefore that's also important. And that's important because these wavelengths have a special importance, which I won't go into. And therefore, you can study the behavior of certain kinds of atoms on the sun's chromosphere just outside the surface, because we now can image the sun in the light emitted or absorbed by those atoms, and that's why it's kind of special. So these are some of the very unique features of Aditya, which other spacecraft launched before have not been able to do, and that's why every solar astronomer around the world and India like super excited.
Okay, sir. Thank you. Now, moving ahead, we have one question from Riti Patel of class 8B from Saint Kabir. Now, she is asking, Aditya L1 is very far from sun. So, with this high technology, can it study its surface also? But how will it going to study the near inner sun?
Okay, now it will study the surface and outwards. But as you can see from the pictures on the right side, it can form a very nice image of the sun, right? It's quite zoomed in, and it can zoom in further, and therefore it will be able to image the sun. It can zoom in, image a part of the sun, just like the solar storm videos and photos I showed you earlier on the top, which are taken by all the older NASA spacecrafts. You can also do the same thing with this as well. So we'll also be able to produce similar images and similar videos with these images as well. Though it's far away, you can magnify it. A telescope's function is, of course, to collect a lot of light, so you can see fainter and fainter things. Its function is also to magnify things, and therefore these telescopes will also magnify the sun's image enough to see what is going on.
Okay, sir. Okay. So we have one question from Manishka of class 9th from GD Goenka Public School, Bahadurgarh. Now she is asking, which discoveries will be made easier after the successful completion of Aditya L1?
Okay. So, if we knew what they were easier, then we won't build it, right? So, idea of building a new telescope is we don't know what it will discover. Discovery is going to be new. That's why everybody's excited, right? But we know roughly what kind of questions we'll be able to answer better because of Aditya. So, one, of course, is how are solar storms produced and how are they initially accelerated? You saw those videos of storms, right? They were ejected at high velocity. So the coronagraph will be able to answer how are the solar storms accelerated in the initial stage. So that's one question we know we'll find some answer to. We'll also find, okay, the other big thing we'll find answer to is how is the corona heated up. And nobody really understands why the corona is very hot. And Aditya L1 hopefully will give you some answers as to why the corona is very hot. That's something, this is a question which is open question. People are doing research on it all over the world, and that's something we might be able to answer.
Okay, thank you, sir. So moving ahead, we have one question from Zoya of class 7 from Trinity English School. Yeah. Now, the question is, what is the basic use of Papa? Can you elaborate a little?
Okay, I had to go to the slide because I forgot it. It's a nice name. It's a very catchy name, of course, right? So, yes. Papa and aspects. Have you heard of mass spectrometer? If not, never mind. So, if you have, let's say in your lab, as you go to high school or college or university, you will encounter instruments where you can put some gas inside and it will tell you what kind of atoms the gas is made of. Okay, it can tell you, oh, this gas is made of oxygen, it has some magnesium, it has some calcium, etc. These are instruments and which will tell you what the gas is made of. They also instruments will tell you what a liquid is made of, what a solid is made of. There are also instruments which you'll encounter in your school laboratory or college laboratory, which will measure the temperature. Temperature, of course, you can measure. You can stick a thermometer into a liquid. But how do you tell the temperature of a solid? It's not easy, right? Or of a gas. So then there are ways of doing that in the laboratory on Earth. So you can measure how hot something is. You can measure how dense something is. Right? You know how to measure, for example, in your high school lab, you will find out density of certain solids. What do? You measure the volume by measuring its, let's say a cylinder, you measure the diameter and the height, and then you calculate the volume, and then you weigh it and you find the mass, and mass by volume is density, right? How do you measure the magnetic field? There are ways of measuring magnetic field also. Now, all of this you can do in the lab for gas, liquid, solid, which you put in the instrument. Now, what do you know? We have talked about the fact that the solar storm, which is plasma, will blow past Aditya L1 and towards the Earth. So these instruments will capture some of the plasma blowing past Aditya. Okay, so it will do the same thing we do on Earth. It will tell you, it will find out what is the density of the plasma. It will tell you how many grams per centimeter cube. It will tell you what the temperature of the plasma is. It will tell you how much magnetic field the plasma has. it will tell you what kinds of elements the plasma has, how much iron, how much hydrogen, how much carbon, how much oxygen, etc. So aspects and papa will do that. That's what aspects and papa will do. It will measure the properties of the plasma as if we went, took the plasma, brought it to Earth's laboratory and studied it. Instead, we had a laboratory in space to do that.
Okay, thank you, sir. I hope you have got the answer of your question. Now, moving ahead, we have Taha from DAV International School. Now, the question is how much kilometer Aditya L1 is away from Earth and why we have only chosen Aditya L1 as a point over here?
Okay. Aditya L1 is 15 lakh kilometers away from the Earth. Okay. So the Sun, if you remember, is 15 crore kilometers away from the Earth. So the Aditya L1 is only 15 lakh kilometers, is 1/100th the distance to the Sun. So that's how far. So this in this figure, not to scale. This figure shows the L1 being very much closer to the Sun. That's not true. If the Earth, if this is Earth, and this is the Sun, Aditya L1 is like here, very close to the Earth. Okay, and it's 1/100th the distance between the Sun and the Earth. Is that the full question? There was a second part of the question. What is it?
Second part was why only L1 is chosen as the point over here, because we have 5 points. So
okay. So why do we choose any of the 5 points? Now we have, for example, satellites going around the Earth like INSAT and all of those, right? You know them, Hubble Space Telescope, INSAT, and all that. GPS satellites and all that, right? So these satellites will go behind the Earth at some point, and therefore they can't see the Sun because they'll be behind the Earth. But you want to look at the Sun all the time, right? If you look at the so L2 is behind Earth, therefore you can't look at the Sun at all. In fact, that's why you have the James Webb Space Telescope on L2, so Earth will protect it from the Sun's radiation. L1 is always between the Earth and the Sun. Sun is here, the Earth goes around the Sun. As the Earth goes around the Sun, the L1 point will also go around the Sun. So L1 will always be between Earth and the Sun, which means that if you put a telescope there, you can look at the Sun 24 hours a day. Okay? That is why some of the other telescopes from NASA to look at the Sun are also in the L1 orbit. L1 already has a few telescopes to look at the Sun. Aditya L1 is joined them because from L1 you can always look at the Sun continuously. That's the reason.
Okay, sir. Thank you. Now, Bhavika from GD Goenka Public School again is asking, is there any specific, the question is there any specific reason why we are continuing watching Corona from the Aditya L1?
Yeah, the reason is because of the solar storms we saw. Sun is very active. Things keep changing all the time. So we need to keep monitoring it. There'll be some sunspot today, it will disappear in 3 days. There'll be a solar storm today, there'll be a solar flare tomorrow. And we need to, therefore, things are always happening on the Sun because things are always happening. Sun, we have to keep looking at it all the time. It's as simple as that.
Okay, sir. So now Munish Kataria from St. Columbo School is asking, has Aditya have any solar panels on it? And if yes, so is there any chances for the solar panels to get destroyed because of the sun and its heat again?
It has solar panels. You can look at this picture. On both sides there are solar panels, right? Solar panels won't get it. Solar panels are designed to use the light from the sun to generate electricity. So you need the sunlight to fall on the solar panels. Almost all spacecraft launched by any country has solar panels, and they function by a phenomenon in physics called photoelectric effect, which you learn in your 10th or 11th class. So the solar panels work because sunlight hits it, and it converts the sunlight into electricity and feeds that into the spacecraft. So that's the function of the solar panel.
Okay, sir. So now Agrim is asking from Shivashish Public School that how long is Aditya L1's lifespan and what is going to be done after that?
So Aditya L1 so everything on Aditya L1 is supposed to function for at least 5 years, but then we think it will function for 10 years maximum. But see, Aditya L1 has so many things. It has 7 different instruments. Each instrument has 2 or 3 things inside. So all of them have to continue working together. So after 5 years, there's no guarantee in some sense, right? Some instrument might degrade, some instrument might not function very well. But for 5 years at least, we know everything will function. It's been designed to work perfectly for at least that long. But we expect that its lifetime will be probably 10 years. And remember, 10 years is interesting because the solar cycle is 11 years, which means we'll study the sun for one whole cycle, which is very important.
Okay. So, Sir Riti Patel is again asking, if any solar storm appears right at the time when it's a full solar eclipse, can we see with the help of that Aditya L1?
Yeah, of course. Yeah. So Aditya L1 will create a solar eclipse all the time. So we will always see it. we'll see all solar storms.
Okay, sir. Now, now there is one question about the costing from Shreyan Rakwal from Sacred Heart Convent School. That
Mhm.
what is the entire cost to make and launch, and then how it's affecting India as a country?
Okay. I don't know the full cost because ISRO doesn't release the full cost, so I don't know for sure. So the cost of what we made, the coronagraph is I think 150 crore or 200 crores. I'm not really sure. Don't quote me on this, though I know it's going on YouTube publicly. It's of that magnitude, and then the other instruments also have come in, and then you have to build the entire spacecraft. So it's a bit more than that. Uh, so maybe 150, 125, 150 crore for one instrument, and then the others as well, right? But the one we made is the most expensive and the largest and the most heaviest. So others will be less than that. So totally would be a few hundred crores, I suppose. But that's and but then most missions of ISRO of roughly of that cost, I think. I don't know exactly. So don't tell people that I said this is an amount. I'm not sure, but yeah, but
No
that's
worries, no worries.
roughly the cost, right? A few hundred crores.
Okay, so now Hardik from GD Goenka Public School is asking a question that is there going to be any other L1 or solar missions in space in future?
We hope so, but then we're just waiting for L1 to start functioning fully. Aditya L1 to start functioning fully. So we are just waiting for the first data from Aditya L1 itself, right? And then we will then use it for years and years and years. But then astronomers are very greedy. We astronomers always want more and more telescopes, larger and larger telescopes. So solar astronomers in India have already started discussing what's next. What is the next instrument? So because space missions take a lot of planning. Okay. So if today me and my colleagues sit and say, okay, we want to launch this kind of space observatory, by the time it's launched, it will take 15, 20 years because we first have to plan it, we design it, that takes a few years. Then we go to ISRO and say, look, this is what we're planning. They will then look at it and say, okay, this is what we can do, we can't do, you come back, then you then design it again and again. And then you start making it. When you make parts of it, then it has to be qualified, you have to do testing. Sometimes you'll discover that your design was not good enough, you go back, redesign, and then you make all of it. Once you make it, then it goes to ISRO, integrate it, test it again, then launch. This period is like easily 10, 15, 20 years, okay, depending on how complicated the instrument is. For example, XPOSAT, which is an X-ray telescope, was launched by ISRO 2 months ago, and that was only I think 5 years, 6 years time to build it and design and build it. Aditya took 15 years. So therefore, if you want something to be launched 20 years ahead, we have to start planning now. So people already started planning. Exactly what it is not known, but it's still in the initial stages. But there'll definitely be a follow-up mission at some point. When you all finish your masters or in a job, there will be a second solar observatory, hopefully.
That's great, sir. So there is one question by Ridhima Shah from St. Kabir School. Now the question is, will the Aditya L1 be affected by all the solar storms and the flares that happens in the space?
Yeah, so we hope so because we want to measure the solar storm properties. But will it get damaged? Not no, because it's been built. It's been built to withstand solar storms. So, for example, the electronics on board modern satellites are what is called space hardened. So you put them through a particular process, you design them differently so that the radiation from the sun doesn't affect them, right? So if you take your normal electronics and send it up, it will get fried. So you had a special electronics which withstands the radiation and so on. So it won't damage Aditya L1, but we'll be able to measure the solar storm, which is why we launched it.
Okay, so now Daksh Jain from class 6A, this will be the last question. Now, this is from DAV Public School BRS. Now, the question is, like, how much kilometer Aditya L1 is away from the sun? Then that's we have already answered. Now,
Yes.
next is how much did it costing? That is also done. I guess mostly we have answered all the questions. We have 1 or 2 minutes. If anybody wants have any other
Sure.
question, can
Of
we
course.
put in the Google form?
And please do get this QR code on your phone, or your parents' phone. This QR code goes to a WhatsApp channel where we put out announcements about various things we do. Okay. And follow us on Twitter, Instagram, YouTube. A few videos on YouTube, on Instagram. We put up a lot of pictures. We even put up photos of beautiful flowers on our campus and so on. So do follow us on social media. I guess you guys are too young to be allowed to have a social media account. So you can ask your parents to follow us.
Okay, so I think this is it about the questions. They are done with the questions. All right, it looks like we have come to the end of the session. Thank you so much, Mr. Neeraj, for your time today. Thank you to all the students for participating in Space India's Space Explorers online interaction with the astronaut and astronomer. Now, this is Rishita Sharma, and I have my best regards to everyone over here. Thank you
Thank
so
you.
much, sir. It was amazing to have you on
Thank
the
you.
call.
Thanks for having